Batteries are used to drive cars, like how gas is used to drive cars as well. It may seem obvious in 2020, however, that would not have been common knowledge even 10 years ago. Not only have the number of people moving to electric vehicles, but the rate at which people are moving to electric vehicles is increasing rapidly. In order to satisfy the demands of electric vehicles, there must be a solution like always. In this case, a major problem generated by the demand is channeling large amounts of electricity to vehicles quickly and efficiently, since efficiency is always directly correlated with money. Even a small increase in efficiency in transferring power to electric vehicles can generate gargantuan impacts on the environment and electricity prices. Today, when electric vehicles get charged at high-speed chargers, they create a small impact on the grid, and if demand gets high, much more money is used than necessary to deliver the same amount of power into a car. Our charging infrastructure is seeing a big growth in the amount of population of people who own electric vehicles. And the problem is most chargers provide approximately 19.2 kilowatts, which takes around 8 hours for giving 200 miles of range, but it varies based off of your car's state of charge and your car itself. This will easily take up a lot of time as you charge more and more, whereas gas cars, it's just a 1 or 2 minute thing to fill up your tank. 50 kilowatts takes 1 hour and 350 kilowatts takes 10 minutes. So there can be a huge time difference based off the amount of power that your vehicle is taking in. However, the problem is chargers typically have high installation costs, material costs, like concrete, for example, and this can lead to barriers into the integration of chargers, specifically fast chargers like what some companies have today, like Tesla. The basic design of a charger is a three-phase AC-DC conversion and then a DC-DC conversion. Three-phase is the sinusoidal wave pattern of the AC current that is being transferred from the grid into the charger, and there's a DC-DC conversion in order to convert the current into a charge that the car can accept. A transformer can convert the AC voltage into DC voltage, and then a DC-DC converter can convert the DC voltage to a different direct current voltage and also protect from power surges. The charging process involves the state of charge to increase as the voltage also increases, rather than keeping either one constant. Involving more current charging stages causes a decrease in efficiency because more conversions are needed to be made between the power supplies that are transferring the electricity, which means more resistance that is dissipating useful energy into heat. The gas station model is difficult for many reasons due to the flexibility in the amount of power that is being drawn from the grid. For example, when there's a lot of demand on the grid and many people all across a certain area are using a lot of electricity at peak times, then that actually creates an increase in demand and affects your ability to charge your car at a charging station as well. Whereas a gas station, they are not susceptible to other external factors. A solution to many of these problems could be an SST-based fast charger. SST transformers are essentially solid state transformers, and unlike the name implies, it's not actually a solid state transformer, but an SST can have direct connections to the grid, which reduces the amount of conversions necessary and increases efficiency. Like we talked about before, a decrease in the amount of resistance and the number of power conversions means more useful energy being transferred into your vehicle. An SST allows for higher power output and lower installation costs. These devices use silicon carbide transistors, and this enables the SSTs to operate at a much higher frequency, which also results in a smaller transformer, which in turn leads to lower material costs. Most of these devices center around 50 kilowatt chargers, which now have around a 98% efficiency and have cut down losses by 60%, which is significant when you're dealing with megawatts and terawatts of electricity being transferred all over the grid into electric cars. The current simulation we have created models a 3-level boost converter with an NPC converter. The initial stages charges the DC capacitors to 1700 volts. The second stage converts the DC voltage into a single-phase AC voltage using the NPC converter we created. In this picture, the box outlined by the red line shows a 3-level NPC boost, which gets the power up to 1700 volts with a 10 kilohertz frequency. The blue box shows the DC to AC conversion using 4 diodes, while the green shows a 60 Hz sine wave conversion. Those waves almost have an 850 volt per peak, which shows minimal loss in energy conversion from the initial energy source. This is due to the fact that typically when power is transferred over high voltages, there's less power loss due to resistance. Future research. An area to be looked at is the reliability of these transformers and the low usage of EVs in the overall power systems category. Another challenge is integrating SSTs into the current grid system and a lack of comprehensive protection against overvoltages and short-circuiting. Current circuit breakers aren't fast enough to prevent significant damage from occurring, so by fixing these, we can make SSTs a much more viable source for getting electricity. As a result, once more car manufacturers or charging companies start utilizing this technology and show that it is possible and reliable, the momentum will increase and more people take advantage of this new technology. It is only a matter of time before electric vehicle charging is taken to a whole new level.